So, as I was saying, good evening, everyone. In this lesson, we'll be treating. This is supposed to be last week's lesson on inorganic chemistry. So, if at any point you guys don't hear me, I would like someone to call the tutor that sends message on the group. Just call normal call so that he'll be able to notify me and I'll be able to know that okay, something is wrong. Do you get me? Hello.
Yes,
Yes,
sir.
sir. Yes, sir.
Okay, so let's just hope that the lesson will go perfectly without any hiccup. So now, as I said, we'll be treating inorganic chemistry, and I think this is one of the portion of chemistry that is very, very to me. I feel it's somehow dicey, and at the same time, it's interesting because it's like the basics of chemistry, like one of the bedrocks of chemistry. If you can understand inorganic chemistry, especially the portion that they're talking about all the elements and their groups individually. Probably some other things that you would do later on in organic chemistry and even in other branches of chemistry would make more sense. Inorganic chemistry is like them trying to tell you how chemistry is one by one. So this is last week's topic, inorganic chemistry. Let's head into the lesson. So inorganic chemistry is the study of inorganic compounds, typically excluding organic compounds. So now, first off, I would like to differentiate between organic compounds and inorganic compounds. So an organic compound is a compound that is made up of carbon and hydrogen together, but not just carbon and hydrogen. Carbon that is having an hybridized form, an hybridized carbon bonded to hydrogen. Once you have that kind of arrangement, you are talking about an organic compound. So, but once it does not have that type of carbon, probably just a normal carbon bonded to hydrogen, you cannot really call it an organic compound. But what distinguishes organic compounds from inorganic compounds is you have an hybridized carbon, you have an hybridized carbon being bonded to hydrogen. So, inorganic compounds are any compound that are not fitting in this particular structure. Any compound that does not have a hybridized carbon bonded to and to the any compound that does not have the hybridized carbon bonded to hydrogen, you cannot call it an organic compound because for you to call it an organic compound, it must have carbon and hydrogen at least. So organic compound, another name for organic compounds are hydrocarbons. So definitely they have to be hydrogen and carbon for it to call it an organic compound. And this carbon in that particular bonding structure must be an hybridized carbon. So inorganic compound is any compound that is not an organic compound. I think I should have tried to lay the ground well on what organic compounds are. So inorganic compounds are compounds that are not organic compounds. They are compounds that are not organic compounds. So in this lesson, we'll be looking at period 3 elements, group 2 elements, sorry, group 1 and group 2 elements, and also we look at group 14 to group 17 elements. So we would focus on their trends or the trends, the possible trends that occur in these groups and the important compounds that are present in this group. So just give me 1 minute. Let me try to remove other distractions. Let me try to remove other distractions. So as I was saying, we'll be treating group 3 elements. We would also be looking at group 1 and group 2 elements, and specifically group 14 to group 16 elements. So let's head into the lesson. So group 3 elements, they are elements that sorry, period 3 elements. I think I was making a mistake. Period 3 elements, not group 3 elements, period 3 elements. So these period 3 elements, they are kind of a special group of elements. And when you talk about groups, when you talk about row and column in periodic table, you're talking about, let me just use my highlighter here. When we're talking about um, rows and column, when we say groups, groups are talking about the periodic table. As many these are the periodic table. We have the periodic table looking like this, divided into two. The first block is divided into two. Then we have a middle block at the center. Then we have 6 blocks at the edge. So this is the typical periodic table, where we have 6 blocks at the left, at the right, 2 blocks at the left. Then at the center, we have this one split into 10 columns. So this is a typical periodic table. And when you see a periodic table like this, sorry, this center line is just like this. You always see it like this, looking like this. When you move along this portion like this, when you look across like this, you're talking about rows. When you're looking across horizontally, you're talking about rows. This is another row, this is another row, this is another row, and so on. So, but when you're talking about columns, or that's when you're talking about row, you're talking about period. So let me start afresh. We have rows and columns. So rows are the ones that are going like this, while columns are the ones that go like this, vertically. Columns go vertically, while rows go horizontally. So now when we talk about rows are the same as periods. So when you're talking about elements, arranging them in rows, you're talking about them as periods, in terms of periods. So we have um, different periods in the periodic table, and they're typically, I would say basically, they are around 5 periods. They are around 5 periods in the periodic table, but they can be more than that. Then for columns, we have 18 columns, that is 18 groups. So horizontally is called period, while vertically is called groups. Horizontal period, vertical groups. So when you have the periodic table arranged like that, I know at some point some people will get confused when they start hearing groups, period. They don't know which of them is which. But the simple thing is just periods are the ones that are going horizontally. Groups are the ones that are coming vertically. So we are dealing with period 3, meaning the third period on the periodic table. So the first period on the periodic table starts with hydrogen and ends with helium. It starts with hydrogen and ends with helium. That's the first period. The second period starts with hydrogen, helium, lithium, then ends with neon. So the second period starts with lithium. Sorry, where's my pen? So the first period starts with hydrogen, then ends with helium. The next starts with lithium, then ends with neon. The third period starts with sodium and ends with argon. So that's the third period. So now we are focusing now on this portion, the third period on the periodic table. The reason why they're focusing on them is because they have special characteristics. They are mostly the elements that you see in most reactive cases, except towards the end of period 2. Period 2, the ending, that's the end of period 2, the one that are towards the ending, they are more used. Then the most used are this period 3. They are the most reactive elements. They are one that most reactions or most inorganic compounds are made up of the period 3 elements. So that's why the focus is always on period 3 elements. So period 3 elements starts from sodium and ends in argon. While non-metals are always on the right, metals on the left, non-metals on the right. So it's important to know this all these things I'm mentioning now, because they would help you to be able to grade and tell which elements are metals and which elements are non-metals. So typically, group 1, group 2 are always metals. Group 1, group 2 are always metals. Group 1, group 2 are always metals, except hydrogen. So group 1, group 2 are always metals except hydrogen. Then when you move from group 2 to group 3, there are 2 ways they could arrange the periodic table. They could arrange them in terms of group 1, group 2, group 3, group 4, group 5. If it is the first 20 elements, they can say group 1 to group 8. But when they're talking about the entire periodic table, you will say it's group 1 to group 18. Group 1 to group 18. when you're talking about the periodic table generally. But if you're talking about the first 20 elements, you will say from group 1 to group 8. So that's why in some textbook you see group 1 to group 8. And typically they will say group I to group VIII. So when they say it like that, they mean that they're talking about just the first 20 elements, or they might even say group IA to group I I group VIIB. That's how they will list it. So meaning they're talking about the first 20 elements. But when you are including every single element, it will be a total of 18 groups in the periodic table. There are a total of 18 groups in the periodic table generally. But when you're looking at just the first 20, they might seem it to be like as if they are just 8. So these groups now, what even made me what I was talking about? I was talking about the groups, their characteristics. Group 1 and group 2, they are usually metals, except hydrogen. While group 3 is also considered metal. Group 1, group 2, they are metals. Group 3 also is considered metals also. Then group 4, they are not really metals, but they are not non-metals. So they call them metalloids because they are in between metals and non-metals. Most of the times, they are in between metals and non-metals. So I would like I don't know, I would have loved to probably use the periodic table or write it out to so you guys would probably see how it is. Sure. Maybe that way it would make more sense. But either ways, let's just move forward. Let me just write it down. Writing it down here will be better. We have group 1, hydrogen, then group this one, hydrogen, helium. Then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then we have sodium, that's Na, sorry, Na, sodium, magnesium, sorry, aluminium, silicon, phosphorus, sulfur, chlorine, argon. So now, why I'm writing this as because I want to, so we'll be able to see what I'm talking about clearly. So now we have this as one group, this as another group. Let me use a different color so it's clear. We'll be seeing the dividing line. So we have this as one group, another group, another group, another group, another group, another group, another group, and that's the end. So from these first three, the first three from this end, the first three starting from your left, they are usually considered to be metals. They are usually considered to be metals. So then coming this way, the ones at the center here, they are usually considered to be metalloids, but they would group them together with this. These two, they consider them to be metalloids. They are neither metals nor non-metals. They usually group them to be metalloids. Then when you then go from this point here, from these two here, they call these two non-metals, or they even call everything here at this end, they call them non-metals. But these two now, they call them, I think they call them, this one they call them the halogens. And this one they call them the chalcogens. That's the ones that have oxygen, sulfur, they call them the chalcogens. While the one that has chlorine, they call them the halogens. So these are the purity is arranged. We have these two here. We call them the alkali metals and the alkali earth metal. While this one here, they call them the rare earth metals. This one's the group 3. Then this one now, they call them metalloids. These two, they are metalloids, but I think they have their individual name, but I've not really the name. Then this one now, they call this one oxygen, the group of oxygen. They call them the chalcogens. Then this one, they call them the halogens. Then the last one, they call them the noble gases. The noble gases. So these groups now, the way you arrange them now, the first three are known as metals. The first three.
Do so.
Yeah. Okay, I think someone was talking to me. So the first three are seen as metals. Then the two at the middle, the one of carbon and nitrogen, they are usually seen as metalloids because they are neither metals nor non-metals. So then the ones going towards the end, they are seen as completely non-metals, completely non-metals. So normally they would always join what they call it sodium. This one here, they will normally join these ones here, the ones that have nitrogen. They normally join these ones to become among the non-metals. They'll call only these ones the metalloids. But sometimes some of them towards the bottom, they are also called metalloids. So that's why I said these two, they are considered to be metalloids. So then this end, the end here, they are always seen as non-metals. They don't have any metallic properties. They don't have any metallic property. So these are the periodic table usually divided into, is typically divided into. First three are seen as metals. The middle ones, the middle two are seen as metalloids. Then the ends are considered as non-metals. Non-metals are noble gases, so they are usually non-metals. Typically, they are all non-metals. So now, there is a trend that always happens across this periodic table. There's a trend that actually happens across the periodic table, and that trend, how does that trend go? When you move from this region down to this region, something happens. The atomic size decreases. That's the size of the atom decreases. Meaning, if hydrogen, or let's use the period 3, because period 3 are the one that are most common, that we see mostly in most inorganic compound. So period 3, sodium. When you take sodium, for instance, the size, let's assume the size of sodium, let's say, let me just use a hypothetical number because it's smaller than this. Let me just say 20 centimeters so we can relate with it. So the size of sodium is 20 centimeters. If you come down to magnesium, magnesium will be smaller, meaning magnesium might be around something like 18 or 17. Coming down to aluminum, it will become small again. Coming down to sulfur, smaller. Chlorine, smaller. Argon, the smallest. So there is always a reduced atomic size going from this end. So they will be having large size here, then coming here to become smaller size. So this is a typical trend. And I think this thing comes out exam, mostly in the objective portion. To try to twist it in one way, but the main idea is just know that the atomic size always decreases from the left to the right along the periodic table. That's when you move from left to right and across a period. Because when you're moving from left to right, you're moving across a period, left to right, across a period, left to right, across a period, left to right, across a period. So when you're moving across a period, because those are the words that we use, moving across a period, what happens to the atomic size? So atomic size decreases when you move from left to right. Atomic size decreases when you move from left to right. And I will explain why, because this explanation of why I think is very, very important, because some other questions could come up from this reason. So they could ask you, the atomic size increases from left to right, or decreases from left to right. Why? So the reason for this decrease is due to the increasing nuclear charge, or the increasing effective nuclear charge. So that's the reason why the size reduced. So what does this effective nuclear charge mean? You know, when we are going along the periodic table, if you have been in the lesson from the beginning, I said, as we are writing numbers, we are moving from hydrogen. Hydrogen is number 1, number 2, number 3. They're going from left to right, 3, 4, 5, 6, 7. So if you look at it, we are increasing in number from left to right. So now, this increase in number that we are going 1, 2, 3, 4, 5, 6, 7, 8, what is actually happening is that the size of the proton, this nucleus, the number of protons in the nucleus is what is increasing by that 1, 2, 3, 4, 5. So because of the number of protons in the nuclear charge, nuclear charge. So because of the number of protons that are increasing in the nuclear charge is also becoming stronger. So once this charge is becoming stronger, it will make it, since the charge of the nucleus is trying to pull the what they call it, the atoms, the electrons in the atom, trying to pull them to itself. I don't know if you've seen something like a black hole. Black hole always tries to draw things into itself. So that's how the nucleus acts. It tries to pull electrons into itself because it's positively charged. The nucleus is positively charged. So it tries to pull negative electrons towards itself. And as it is trying to pull them towards itself, that ring that those electrons move around begins to reduce in size. And that ring is what is responsible for the size of this electron, for these atoms. So if the nuclear charge is increasing, meaning the pull from the center on those rings is becoming stronger, means that the ring will not be able to expand wide, to become smaller in size. So this is the reason why the atomic size reduces across the period. I don't know if this makes sense to anybody. Can you guys still hear me? Hello, can anyone hear me?
Yes, sir, we can hear you.
Okay, good. So that's how the nuclear charge, that is reason for the atomic size to decrease across the period. So now, talking about this same atomic size now, I've talked about atomic size across the period now. This same atomic size going down the group on the periodic table, it is seen to increase. I think I've talked about this thing when we talked about the periodic table earlier in the nice class. When you talked about, I will not really spend much time because I think I remember we talked about this, so we'll not really waste more or spend more time here when it's something we talked about in details before. So when you go down the group, atomic size increases, and the reason for the increase is because of the increasing nuclear charge also. So sorry, increasing number of shells. So as the number of shells are increasing, because hydrogen has just one shell, lithium has two shells, um, sodium has three shells, because as they're moving down like that, the shells are increasing. Each period is telling you if it is period one, it means there's one shell. Period two means there are two shells. Period three is telling you there are three shells. Period four, four shells. So as you go downward, the shell is increasing, meaning the rings are increasing more and more. So since the rings are increasing, definitely the size will be increasing as you move down, because one ring, two rings that where one is swallowing the other one, three rings where the third one is swallowing the other two, definitely the sizes will be increasing. So that's why the atomic size reduces down. So ionization energy also increases, it's set to increase. So ionization energy, if you can remember from our lesson when we we're talking about the periodic table, it is the energy required to give off an electron. To give off an electron. The energy required to give off an electron. So when someone is stingy, it will take the person more to give off money. Someone that is stingy to give money will be very, very, very hard for the person. So metals, they are seen to be free-handed. They easily give electrons. While non-metals, they are seen to be stingy. They don't like giving, they prefer collecting. So they are seen to be somehow stingy if you're trying to use human or trying to personify them. Metals are seen to be givers, while non-metals are seen to be stingy receivers. They only like to receive, they don't like giving out. So because of that, because they are stingy, for them to give, if they say it is compulsory for everybody to give, they will be seen to spend more energy trying to give, have many contemplation before they would give anything. So meaning the ionization energy now for metals, the number of trying to convince them, the number of words you talk to metals, that's the ones at this area, the number of statements you tell them will be less compared to the ones that are trying to convince a stingy person to give. You will not really preach so much when you're trying to talk to a giver to give you. But if you're talking to a stingy person to give you, you will preach, you quote, 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 quote. You will talk tire. So that's how the energy is relating to this. Non-metals, you need more energy to make them even give out just an electron. And ionization energy is talking about the energy to give off an electron. So that is the reason why ionization energy increases down the group, because as you go down, they become more stingy and their tendency to give up becomes lesser. So due to the tendency to give up electron reducing across the period, that's the reason why ionization energy increases as you go down the group. So electronegativity also, electronegativity on the other end is the, and what they call it, the ability to gain electron or to receive. Electronegativity is talking about their charge, like the negative charge on these electrons. So now, when you look at sodium now, sodium in its outermost shell, it has just one electron in its outermost shell. But if you go down to argon, it has 8 electrons in its outermost shell. So because of this increase in electron, and electrons are negatively charged. So because of this increasing increasing negative value on these atoms, you can say that the electronegativity is increasing as you go down because sodium has one electron in its atomic shell. This one has two. The next has three. So the negativity is increasing more because electrons represent negativity. So this electronegativity increases as you go from left to right. That's across the period. So I also hope everyone happens to get what I was trying to explain. Is getting what I'm trying to explain. So can you guys still hear me before I move on to the next slide?
Yes, sir, I can hear you.
Okay. So now let's move on to some of the compounds that are made from this period three. Period three are these ones here, where we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So we're now trying to look at compounds that are made from these period three elements. So now, one of the compounds is sodium hydroxide, made from sodium reacting with oxygen. Sodium reacting with oxygen. So this compound is known as an oxide, sodium oxide. So it's very, very reactive. Very, very reactive. So when it reacts with water, it reacts with water vigorously. And when it reacts, it forms sodium hydroxide. So this is one of the ways they usually use to produce sodium hydroxide, caustic soda. So when you react sodium oxide, that's Na2O, with water, you will get sodium, hydroxide. So the next one is silicon dioxide. So now, when you react, this particular one, it's sand. Silicon dioxide is sand. Pure sand is silicon oxide or silicon dioxide. So when you have silicon oxide, if you notice sand, if you try to dissolve real sand, not dust, sand, grain, like real sand, if you try to pour it inside water, it cannot dissolve inside water. So it is insoluble in water. That's one of the properties of this sand. And one thing you should take when you talk about sand, one of the reactions or one of the major use of sand, it is in the production of glass. If you don't know, they use sand to produce glass. They would wash the sand and wash the sand in the industry. They will wash the sand. When it is now pure, they will now react with sodium triisocarbonate under heat, and it will form glass. So one of the compounds that are one of the major compounds in what they call it, formed from the period three elements, sodium and the major uses for glass production. Another one that is very, very important as a member of this group, or this period rather, is phosphorus pentachloride, PCl5. So this PCl5 is one of the reagents that they use majorly when you are trying to, in organic compounds or in organic chemistry, when you're trying to carry out halogenation, especially with chlorine, you would use phosphorus pentachloride. So they would always carry this reaction in the presence of UV light. They will react any what they call it, organic compound, usually alkane. They will react them with alkanes, and they would undergo substitution reaction with alkanes to give you halo alkanes. So the compound that is used for this process is known as phosphorus pentachloride. So this is one of this compound that I'm listing out here are the important compounds from period three, from the period three and on the periodic table. So usually you would see that they are always asking you for their uses or these compounds, major use cases. So the major use case of this phosphorus pentachloride is as a chlorinating agent. It is used as a chlorinating agent, while silicon dioxide is used in production of glass. Sodium oxide is used in the manufacturing or the production of sodium hydroxide. So then the fourth one is sulfur dioxide. So sulfur dioxide. So this one is gotten from the combustion of sulfur. So when you burn pure sulfur in air, it forms sulfur dioxide. And I think this one is one of the compounds that are used in production of work. I think they call it workhorse or horse work. That's what they call them of this compound. H2SO4. SO2 is one of the raw materials for production of H2SO4. So sulfur dioxide is gotten how they produce this is from the what they call it from the combustion of pure sulfur. They will burn pure sulfur in air, and once they burn it in air, it will give sulfur dioxide. So these are important compounds from the period three. So these compounds are selected. I selected these compounds specifically because I have found out that these compounds are very, very, very crucial compounds. Because if we want to go down deep, in depth rather, to talk about all the elements or all the compounds in the periodic table, we might end up talking about the ones that are relevant and those that are not relevant. But these ones are the ones that are most important according to my pick. So if you have any other compound, probably that you have or somewhere you feel like, okay, this one, I know this one, and I think I want us to know about this, just mention it now before I move on to the next slide.
Okay, hello, sir.
Okay.
Okay,
Yeah, I can
can you
hear you.
please talk on aluminum 3 oxide?
Okay, that's bauxite.
Yes, okay,
Okay, it is
bauxite.
used in it is used in I think it is used in furnace in usually it is used in what they call in that process. Oh, Chimo. They usually use it in the process of this process that they usually use is not cast iron in making of in iron metal production. They use it in one of the electrolysis, yes, one of the electrolysis process. They use it in smelting of iron. I think they use it very well in iron. Bauxite, it is made up of aluminium trials, that's Al2O3. Bauxite is one of the very, very important chemical, one of the important compounds from this group, bauxite. It's an ore of aluminium, and it's usually found together with water of crystallization, usually Al2O3.5H2O, usually. So they use it in electrolysis in most electrolysis process. They use it in most electrolysis process, and it is also used in I think it's in the production of cast iron, if I'm correct. But they use it in furnace, usually in furnace. There's one popular I don't know why it's slipping my mind. One popular um metal that they use it for the electrolysis of that metal. I think it's iron or calcium, one of them. I would confirm it, sure. But bauxite is one of the major elements in they use in one of the major compound that they use in metal industries for electrolysis and also as what they call it in electrolysis, and also they use in I think they use as a catalyst in some processes. Sha. So it's one of the important products from aluminium oxide.
All right,
So
thank you, sir.
Al2O3.
That's it.
Yeah, you're
Thank you.
welcome. So any other one. I think we have calcium triazocarbonate. But I think calcium is on four. So calcium triazocarbonate is another important one. That one is used in limestone, and they use it to produce calcium. It is produced from calcium oxide. I think when you react it with, I think if you burn it in air, you get calcium, or when you expose it to air, you will get calcium triazocarbonate, CaCO3. Yeah. So these are important chemicals, but we're talking about specifically the ones from period three. We've talked about sodium, magnesium sulfate. That's MgSO4 is another one. But that one they use it in I think they use it magnesium ribbon they mix it together in production of one compound, one of these major processes. They use it as a catalyst in one of the major processes, magnesium, but it's not really popular like that. Magnesium MgSO4. So these are like the major compounds from the period three. Sodium, sodium hydroxide, that's one of the key compounds. Sodium hydroxide, very, very, very important. They use it in many titration processes as a major base. Sodium hydroxide is used as a major base. Then we have aluminium triazocarbonate in metal industry. It is used very, very well in all purification. Yes, in purification of metals, they use it in what they call it electrolysis. In some electrolysis process, they use it as one of the electrodes majorly. Then I think we have these ones I also mentioned: silicon dioxide, phosphorus pentachloride. Um, yeah, I think these are important, very, very important period three compounds that you just should take note of because if they would want to ask you about period three and some of the compounds in period three, these are the compounds that they will ask you for their use cases. For their use cases. So now let's look at hydrogen. Hydrogen. So hydrogen is a light element. That is the group one element. And hydrogen sometimes is seen as, it is seen to have three isotopes. The first one being protium, the second one being deuterium, and the third one being tritium. So they will, sometimes you see it as proton, you say it's proton, deuterium, and tritium. So these are the three isotopes of hydrogen. That's the three forms that hydrogen exists as. So hydrogen is the first element on the periodic table, having just one electron, one electron, and usually one proton. It has one proton generally. Every time it always has one proton. So hydrogen always has one proton every single time. And there are some cases where if you have one proton and that proton is unit it has, that's when you have proton. When it is seen as proton, hydrogen as proton, it's H1, mass number one, atomic number one. That's one up, one down. That's H. In that case, it is acting as proton. His name is proton. So now, when it now has a mass number of two, that it has one proton and one neutron. In that case, it is called deuterium. Then when it goes to three, that's when it has the same one proton, but now in this case, now two neutrons. It's seen as tritium. So typically, it is the group one element. Sometimes they see it as halfly filled. They see it as a halfly filled gas, because normally it's supposed to, in its own orbital, in its own shell, in the first shell, it's always supposed to have two. So it's supposed to have two, but it has just one. So half of two is one now. So it's usually seen as a half filled metal. It's partially filled. Sorry, as a partially filled element. So in some cases they will see it as a partially filled element. In some cases they'll see it as an incomplete element. Yeah. So, but that's hydrogen, and it's a very, very, very important compound in the periodic table. It is usually formed from reactions that occurs in the sun. One of the major source of hydrogen gas is from the sun. The reaction that occurs on the sun. So it is used as fuel in fuel cells. It's used as fuel in fuel cells, and it is one of the bedrocks for organic compounds. As I said, organic compounds are made up of carbon, that's hybridized carbon, and hydrogen. So if there is no hydrogen, you're not talking about an organic compound. So it is one of the core functions, core elements in the periodic table. Water is made up of hydrogen. Most elements, they can react with hydrogen. So it is very reactive. Hydrogen is very reactive. I think it is one of the most reactive too. It's among one of the most reactive positive elements. One of the most reactive positive elements. It has the highest, like one of the highest tendencies to give off electrons, because it has just one electron, usually in most cases. So it has just one electron, yes, one electron. So hydrogen, it is the lightest element. It is the lightest element on the periodic table, and it exists as hydrogen gas. So the properties of this hydrogen is that it is colorless, it's odorless, and it is flammable, that it can catch fire. So it is used in fuel cells, as I said. It is one of the very strong reducing agents. It's one of the strong reducing agents. So take note, metals are known to be reducing agents. Metals are known to be reducing agents, while non-metals typically they are seen to be oxidizing agents. So they are known to be oxidizing agents. So reducing agents, they are usually oxidized, while oxidizing agents are being reduced. So reducing agents are usually oxidized. Oxidizing agents are usually reduced. So metals are known to be reducing agents. So they are known to be reducing agents, meaning that they usually undergo oxidation, and oxidation is the loss of electrons. So in metals, they lose electrons, while non-metals, they gain electrons. Reduction is the gain of electrons. Oxidation is the loss of electrons. So just, I'm mentioning this thing because I think it's something that you should get familiar with. So they are using the hydrogenation of oils. So when you have unsaturated hydrocarbons, hydrogen is one of the is usually what they use to hydrogenate these unsaturated hydrocarbons, typically for the olefins and I think the acetylene. That's the alkenes and alkynes. So they are used. It is used in the hydrogenation of these oils. So hydrogen is very, very, very important. One of the very important elements in the periodic table. Is very important, and it's very reactive. It's a very strong reducing agent. So there are different types of hydrogen forms that it appears as. So when hydrogen is reacting with metals, when hydrogen now is reacting with metals, it forms what is known as hydride. Hydride. When you see any metal bonded to hydrogen, it's seen as a hydride. A hydride. So when like now you can see lithium aluminum um tetrahydride. It's called an hydride because we're having metals being bonded to hydrogen. So when we have the typical metals, alkaline metals or alkaline earth metals bonding with hydrogen, they form hydride, especially when they form ionic bonds, they form hydride. So now when we have hydrogen now forming with what they call it, with non-metals, we don't call it hydrides like that. We don't call it hydrides. When we get them, we'll see what they are called. But typically, when we have hydrogen that is bonding with what they call it, bonding with metals, it is usually called hydrides. So when it is like when you have hydrogen and chlorine, you would not really call it a hydride per se. The word hydride is typically used when it is bonded mostly. Some people can call it hydride, but typically it is called hydride when it is bonding with a metal, typically. So these hydrides are used for using hydrogen storage. They are used to store hydrogen. As they are used as fuels. If you need hydrogen, you just use these hydrides. Like typical, like one of the common hydride is lithium aluminum tetrahydride, LiAlH4. So when they say that hydrides are used to store hydrogen, means they are used to hold hydrogen. So that if you now expose them to somewhere that needs hydrogen, they will easily give up the hydrogen without stress. So they are seen as hydrogen storages, or they are seen as hydrogen stores, hydrides. They're seen as hydrogen stores. And because of they are seen as hydrogen stores, they are called reducing agents. So hydrides are usually reducing agents. They are usually reducing agents, and they are used in fuel cells. So um, one of the use cases of this hydrogen, which I mentioned before, is the hydrogenation of oils. When you have oils, especially oils from unsaturated hydrocarbons like olefins or alkenes and acetylenes or alkynes, to hydrogenate them, to make them completely saturated, you react them with hydrogen. You react them with hydrogen so they will form saturated fats or saturated compounds. So it's a very, very important process. Food industry, I think hydrogenation process is one of the important processes. And that's how they use to differentiate different oil. Because one thing about unsaturated oil is that sometimes they have tendencies to be I think they are light, but the hydrogenated oils are thicker. They are usually thicker. They have the advantage and they are disadvantage. Unsaturated oils, they have advantages and disadvantages. They are very light. So in cases where you need light oils, you cannot use unsaturated oil. But when you need a thick oil, you go to saturated compounds, or you use saturated oils. So, but in case where you now need where your need is unsaturated, you will need a saturated. How am I even trying to put it? Just take the idea. When we go to organic chemistry, I will break it down properly. But the real sense that we're trying to talk about here is hydrogens are used for the hydrogenations of oils. That's unsaturated hydrocarbons, converting them into saturated hydrocarbons. So, does anybody have any questions so far on what we've been talking about before I move to group one and group two, the general properties of group one and group two elements? Can you guys hear me?
Yes, sir, I can hear you. About the hydrides, you're talking about you said hydrogen, hydrogen and a non-metal when they form together, they're normally called hydrides. So you said there's another name they call hydrogen and a non-metal or something. I don't know if you
Yeah,
stated that person.
yeah. When you have hydrogen and something like chlorine, you don't necessarily call it an hydride per se, but generally they call anything that is bonded with hydrogen, they call it an hydride. They call it hydrides. They call them hydrides rather. So, but in most cases, you will not already see them in some textbooks. You will not see them being called hydrides. When they talk about hydrides, they call them separate. They call hydrides separately. The metals of group one and group two bonding to hydrogen. They call them hydrides. So those other ones now, they could be seen as it could be seen as if I can remember, they are seen sometimes as acids in some cases. When you see hydrogen bonding with non-metals, hydrogen with bromine, you call it an acid. Hydrogen with um, some kind of bonding with let me see, hydrogen and sulfur, like hydrogen H2SO4, you call it an acid. You cannot call it typically a hydride. You cannot call it typically a hydride. So you call it an acid because it has hydrogen bonded to other compounds. So you not really call it an hydride. H2S, hydrogen and sulfur. You not really call it an hydride like that. You not really call it an hydride, but it's really an hydride in general definition, combination of anything with hydrogen. But typically, what they call hydrides in some textbooks, some advanced textbooks, would always call hydrides anything with metal in ionic bond with hydrogen. So hydrides are usually called hydrides when hydrogen is acting like a negative species. You will always call it hydride when hydrogen acts as a negative species, because when you have sodium bonded to hydrogen, in that case, sodium is not ever going to accept electron. It's always going to give an electron. So meaning in those cases where hydrogens are accepting electron, they are usually considered to be hydrides. And it's usually when hydrogen is bonded with metals that it accepts electron. So when it is giving up electron, when it's bonding with non-metals, they don't really call it hydride in most textbooks. You get? So
All
when
right,
hydrogen
I
is
get.
acting
Thank
like a female, when it's acting like a female, that's the typical definition of when you call hydrogen an hydride. That's when it's accepting electrons. It is typically called an hydride, not an anhydride. There is something like an anhydride, but just it's hydride. So pardon me, I'm using the tongue twister word. Yeah.
I
So it is
understand. I
called,
understand. Thank you, sir.
yeah. So let's move forward. So general properties of group one and group two elements. Group one elements, they are, as I said before, they are usually called the alkali metals. And most cases, they would always, if you look at some periodic, they will always isolate hydrogen and helium because they don't really behave very well like rest downwards because of they don't have similar number of shells. Their shell is completely different from the rest. Other ones will have 8 and above, but then they have just 2. So their behaviors are completely different from the rest of the members of their own group. So typically, the alkali metals, they are always seen from lithium, the period of lithium downwards. So these alkali metals, they are called, they are members from the group 1 element. Group 1 element. So the next one after them is the alkaline line, Line, alkaline earth metals. That's the group 2 element. That's this one is even here, the name is here. Alkaline earth metals. So these alkaline metals, they are very, very reactive, especially with water. Like lithium, if you put lithium in water, one way you can cause explosion is putting lithium in water. It reacts vigorously, like seriously, with water. It reacts vigorously. This is one of the properties of these alkaline metals. Even sodium, putting sodium in water to catch fire. So if there's one way they say they want you to, if you want to set, this is one thing I think chemists they can use to set a particular house on fire. I think there was one movie I saw it where the movie they wanted to set a particular building on fire, but they know that if you carry something that is like fuel, the building has water resistance. The building, once any fire comes out, the building would immediately the water service or the water system will start pouring out water. Once there's any form of excess heat, it start pouring out water. So the guys that were trying to burn down that building, what they did, they went into the building. You cannot carry anything explosive now. You cannot burn that kind of building. It's a very, very tall building. I think it's one of the movies that the rock carpet. It's a very tall building. You cannot carry any explosive because it's a very hard guarded building. So they carried in sodium in bags. So when they tested them, they were not looking like something that is destructive, just sodium. So nobody's mind will go that this thing can be something that could cause fire. So now what these guys did, they carried bags of sodium. They went to the middle floor and they loaded it there. Loaded this sodium there, pour them on the floor, put it on the floor, tear the bag open. Then what they did, I think, yeah, sodium. Then what they then did was when they now had put it there, they now came downstairs and took just lighter. and lit fire lighter near one of the fire sensors, the heat sensors. And once heat sensors sense high heat, it would turn on all the water system, all the water sources to start pouring out water. So now, as these things, well, they were thinking that maybe it is security. What's happening? It seems like fire is on the house. The fire has not actually started. They were doing just on lighter towards the sensor, and see now set water to start flowing up. So as water started flowing up, everybody will be like, "Oh, if there's a fire, that means the water system will try to save it." But they did not even know that it was the water system that is going to even cause the fire to happen, because when water reacts with sodium, there's a serious level of explosion. Like you cannot stay close to it because it sound like bomb, especially if the quantity of sodium is very much. So lithium is even worse when it comes to lithium. So lithium, sometimes even holding lithium on your hand, water on your hand can make it explode on your hand. Sweat from your hand can make it explode. So lithium is very reactive with water. These metals of the group one elements, they are very reactive with water, especially lithium and sodium. Potassium is not as reactive as that, but lithium and sodium are very reactive. So this is one of the key properties of the group one element. So they are highly reactive and they have low melting points. They have low melting point and they form oxide, basic oxide. That is, they form oxides that are bases most of the time when they react with oxygen. They form basic oxides when they react with oxygen. So these are major properties of this group one and group one element specifically. So for the group two elements, it starts from beryllium downwards, beryllium downwards. So they did not exempt anyone on this group. So beryllium downwards. So beryllium, magnesium, calcium, strontium, and I think yeah, that's the name of that one, strontium. Yeah. Then barium. These elements, they are less reactive when you compare them to the one element. They are reactive, but when you compare them to one element, they are less reactive, and they typically form basic oxide, and they have a higher melting point in comparison to the one element. So they are usually seen as like relatives sometimes. So when they form ions, this is another thing I'm mentioning. Group one elements, when they form ions, they form ions. They form a single charge ion, positively charged, a singly positive charge ion. That's when you see lithium. Lithium ion always have plus one. Sodium ion will always have plus one. Potassium ion will always have plus one. You get, so that's like even rubidium ion will also have plus one. So for group two, they would always be divalent. Sorry, pardon me. They will always be divalent. Be would have plus two, Mg would have plus two, Ca would have plus two, Sr would have plus two, and going downwards. So that's how they behave. They have this kind of continuous behavior. So there's something that they call diagonal relationship, but we'll not be treating it for now. But there's a diagonal relationship where some of the elements in one group behaves like elements in the other group. So, but that's not, we'll not be going there yet. So now some of the trends in these group one elements, as I said, the react increases down the group. Reactivity increases down the group. So I think it should be decreases. This should be decreases, because the ones that are at the top, they are very reactive. And as you go down, they become less reactive. So it should be decreases. Reactivity decreases down the group. So alkali metals, they react vigorously with water, which is what I mentioned. They react very vigorously, very vigorously with water to form alkaline hydroxides. To form alkaline hydroxide, that's basic hydroxides. So when they react with water, they form basic hydroxide like KOH, NaOH, lithium. I think lithium does not even form, it does not even allow itself to form LiOH because of the level of reactivity. Instead, to form lithium oxide, Li2O. So that's for these elements. So for group two, the popular trend across group two is that the reactivity increases down the group, but is less vigorous than one. I don't know why. I don't know if this is an error. I don't know if this is an error, but I think the reactivity is supposed to decrease down the group. Okay, no, it increases down the group because beryllium is less reactive comparing it to magnesium. Magnesium is less reactive comparing it to calcium and going down. But I think there's always a peak where they get to and they will start reversing downward. I think it start reversing downward. So it's kind of like a peak kind of movement. You go downward to first start from the top, increasing, then it gets to a point where it reduces. It will increase and it gets to a point where it will reduce. So that's how the reactivity is. So it's not really a continuous trend. It's a kind of varying trend. Coming down from the top, it reduces, then it gets to a peak, then it kind of stays stagnant, sort of. So now, when we now look at these group two metals, they react with water also to form hydroxides, but they are not as vigorous as group one. They react harshly with water too, but not as serious as group one elements. So the group two elements are used in alloys and in construction industry, usually metal construction industries that I was trying to talk about. So they are used in alloying companies, people that are trying to mix metals together, because these elements, they are smaller than the group one elements, so they are used in alloys most times. They have good properties, and for that reason, they would see them as good used metals to blend with other more expensive metals. So their color also, I think the color is something that you can find out. They are typically white. Most of the times, they are typically white. Group two elements, they are typically white. The same with group one. Some of them are shiny. Some of the group one elements are shiny, like lithium. But going down, it's kind of more white. They are more of white colors. So now, extraction of alkali metals, extraction of group one elements. So now, for alkali metals, they are extracted by electrolysis of their molten salts. This is what I was talking about. They are they are gotten how you can get sodium most of the times, even potassium most of the times, by electrolysis of their molten salts. What they mean by molten salt is thick concentration or high concentration of salt that is almost looking like as if it is solid salt. So when you electrolyze these solid salts, you would get metals. These metals, the metals that are bonded with this salt. If you have a molten NaCl, that is also called brine. If you electrolyze it, it would give you sodium metal, because electrolysis always separates the salt into sodium and chlorine, and also water into hydrogen and hydroxide. So when you electrolyze it very well, you would have sodium being deposited on one of the cathode, while chlorine will be deposited on the anode. So that's how you use them. That's how they get these group one elements. They typically get them from electrolyzing their conch concentration salts. So I think another another thing to know about the extraction is high energy is required due to the low ionization energy of alkali metals. So they have they have low ionization energy, which is what I was trying to tell you. The convention that, like, trying to tell them to give off an electron, it is not hard for you to tell them to give off an electron. So they will easily give off an electron to any negative, and usually their source are negative, so they would easily want to give up the electrons. So to force them split is difficult. So you need more energy to cause them to stop wanting to give, or to stay on their own, or to break. So high energy is usually required to separate them. That's why they even need electrolysis in the first place. We use high voltage electrolysis systems to separate them from their salts. So for group two elements, like the alkaline earth metals, they are extracted through electrolysis of their ores the same way, but this one now is electrolysis of their ores. So you could get them by electrolysis of their ores, or by reductions of their oxides. So if you reduce the oxide, like let's say we have calcium. If you reduce calcium oxides, if you reduce it, that's reacting with something that has hydrogen or dehydride, you can be able to go and get calcium metal. So that's one of the ways you can reduce, or you can get these metals as pure metals. So group two, they are usually gotten as pure metal. They're usually extracted by either electrolysis of their ore, or reduction of their oxides. Electrolysis of their ore, or reduction of their oxides. So these are the one of the ways. These are like the two major ways of getting these metals in their pure forms. So now, does anyone have any question before we move forward? I don't know how much time we still have left. Okay, we still have some minutes. So does anyone have any question before we move forward? Can you guys still hear me?
Yes, I can hear you.
Okay. So now let's go on to group 14 elements. So group 14 elements is the elements where you would see carbon, silicon, germanium, tin, and lead. That I think if it is to be in the group the normal 8 group series, it will be group 4 elements. So in other places you see them as group 14. So group 4 or group 14 elements. So they are usually carbon, silicon, germanium, tin, and lead. So these compounds, they are, I can say they are they see them as metalloids or semiconductors. They are neither metallic or non-metallic. That's why they call them metalloids. They are they behave somehow like metals and they behave somehow like non-metals. So their behaviors are just like the variant. So they call them semiconductors. So and that's the reason why they use silicon for chips because it's a very good semiconductor. Very, very good. The same thing with tin. Though tin is expensive, so they don't use tin. But silicon and tin, they are very good semiconductors. So the lower groups, member of this group downwards, they are poisonous. They are poisonous. That's lead. They are poisonous when they are being exposed into the human body. They are poisonous. So carbon, starting with carbon, it's one of the bases for hydrocarbons. One of the bases for hydrocarbons. So it forms many compounds. Carbon is very, very reactive with many. It has like majority of compounds are made with carbon because of organic compounds are typically have every organic compound, even us as humans, our skin, our beards, our eyes, everything, almost everything in our body is a combination of carbon and hydrogen. So long as we are living beings and that particular thing grows, it's a combination of carbon and hydrogen. So that's why they call them organic because they are alive. So every living being is made up of carbon. Plants and animals are always made up of carbon and hydrogen. It might be carbon, hydrogen, and nitrogen, or carbon, hydrogen, nitrogen, and oxygen. But anyhow, they would always be carbon and hydrogen for it to be part of an organic compound. So even our nails is made up of carbon. So for this reason, carbon forms many compounds, many compounds. So silicon now is used mostly in as semiconductors, mostly. If you talk about silicon, mostly they use in glass making and dioxide in glass making and as a semiconductor. Then tin, on the other hand, is typically for soldering. That's all these people that repair phone, that solder stuff, or all these engineers that solder stuff. Tin, that's one of the major use of tin. Is used in soldering. Is used in soldering. Germanium is expensive, but they use it in also circuits. They use it in circuits. Germanium it's expensive, but they use it in circuits, and it's not really that abundant like that. So these are the major uses of this one. So lead is also it's used in different cases also. It's used in some kind of tests. It's used in some tests for solubility or qualitative analysis. It's used as qualitative, but it's also poisonous in the human body in a reasonable quantity. It can be poisonous to the human body. It behaves like the members of arsenic group, stibnite, arsenic. It behaves like them. So going to group 15. Group 15 is where we have nitrogen, phosphorus, and the rest. Nitrogen, phosphorus. So nitrogen is said to be diatomic. So when you hear diatomic, it means you have the same element bonding with itself, the same element bonding with itself alone to form a single atom or to form a single compound. The same element, like oxygen, is diatomic because you can see oxygen and oxygen bonding to give you O2. Chlorine is diatomic because you can see chlorine and chlorine bonding together to give you Cl2. Hydrogen is diatomic because you can see hydrogen and hydrogen bonding together to give you H2. So all those elements that they can join with themselves to form a single um, compound, they are known as diatomic compounds or diatomic molecules rather. So in this diatomic form, it is inert, is unreactive, and it is typically used in fertilizer. So one of the major use of of sodium, sorry, what am I saying? Major use of nitrogen, sorry, is in the production of fertilizers, NPK fertilizers, N representing nitrogen. Even in what they call it during thunderstorm on the root nodules of plants. So nitrogen is always um, when lightning strike, there are these bacteria that they call nitrogen fixing bacteria. They try to aid growth on these roots or in the growth of they aid plant growth. So nitrogen is typically used for this thing fertilizer production, and it is I think it is one of the metals that are one of sorry, not metals, one of the gases that the liquid nitrogen is used as a coolant because it can be very, very, very cold. Liquid nitrogen. So phosphorus, on the other hand, now it forms multiple oxides. Multiple oxides. You can see it as um, P4O10. Same thing has different has variable oxidation number. So you see it forms several oxides because of its variable oxidation number. So and it is very, very essential in biological systems. Phosphorus. So these are majorly the common group 15 elements. If you go down, you will see other ones like antimony, that's stibnite, arsenic. Yeah, you see arsenic, you see stibnite, and some other ones downwards. If you go them in this particular group, so they are typically you don't really see their use most of the times. So, but when you go down, this antimony and arsenic, they are very, very poisonous. They are poisonous as well. Putting them in food, as putting arsenic in any food, the person that eats it will definitely die. Especially even if it's a small quantity, the person would most likely die because it's very, very poisonous to the human system. So, having said that, now we'll be moving to the group 16 element. I'm trying to hurry up because of time. Let me see how much we still have left. Wow, wow. Okay. Still have a reasonable number, but we are going to oxygen. So oxygen is essential in respiration. We know oxygen very well. A lot of us we interact with oxygen every day. It's used in combustion. It's used for respiration. It's used in several processes. Several processes. It forms one of the bases for most compounds, most oxides. It's the foundation of oxides. It's highly oxidizing. So it's like the opposite of hydrogen. Oxygen is like the opposite of hydrogen is a very strong reducing agent. Oxygen is a very strong oxidizing agent. So another member of that group where oxygen belongs is sulfur. So sulfur, it forms sulfur oxide when you burn it, and this sulfur oxide is used in formation of sulfuric acid, which is called workhorse. Sulfuric acid H2SO4 is one very, 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 very powerful chemical, industrial chemical H2SO4. They use it in most industrial cases. That's why they call it workhorse. So it is used in industries, and both of these elements they form acidic oxides. So when they react with oxygen, and this oxygen react, and their output reacts with hydrogen, they form acidic oxides. So like when you can see it in the case of H2CO3, H3PO, H3PO4, you can see it in the case of H2SO4. So those compounds that are forming, we have group when you have oxides of S and O reacting with hydrogen, they usually form kind of acidic oxide, especially when they are bonding with oxygen, acidic oxide, or they form acids when they react with hydrogen, like H2S is hydrogen sulfide gas. It's an acidic gas. So they usually form acids most of the cases when they react with hydrogen. They usually form acids or acidic oxides. So now moving forward into halogens. We know halogen. I think halogen is one of the common periodic table elements. They are very, very common. And you have fluorine, chlorine, bromine, iodine, and yeah, I think these are the major ones. These are the major what they call it, the major groups of 17 elements. So we have fluorine, chlorine, bromine, iodine, astatine. So they are highly reactive. They're highly reactive and they form salts when they react with metals. So these are important things to take note of when you have halogens reacting with metals, especially group 1 metals. They form salts. They form salts. So one major use of, and they are usually diatomic. So these are another property of these halogens. They are diatomic. You can see Br2, you can see I2, you can see astatine 2. You can see F2. So these guys, they are typically diatomic in most of the cases. So chlorine is used as a disinfecting agent. It's used in disinfectants. Iodine is also used as a disinfectant. So they are typically used for um, different pharmaceutical processes. Chlorine, iodine. We even know iodine. Some when they get injured, they rub iodine on that particular point. Even when you cut your hair, sometimes they will rub iodine on your hair. Think so. Yeah, if you take a rough shave or you go to the barbing salon, sometimes they rub iodine so that it will help to disinfect whatsoever germ that probably might want to get through your hair, the cuts, the maybe possible cuts from the blade of the clipper. So they are used as disinfectants in most cases. They form acids when they react with hydrogen. They form acids when they react with hydrogen. And fluorine is very, very reactive and is the number one member of this halogen, and it is very reactive on its own. When it stands as fluorine as its own, it is the most reactive element on the periodic table. The most reactive element on the periodic table and the most electronegative. So these are their properties typically. So now, as I said, they form halides. They form salts when they react with metals, like we can see in NaCl, KBr, KCl, and so on. So the they are important in different industrial processes. They are used in different industrial processes, as you can see in iodine and bromine, and even chlorine. Chlorine, if you even know, in sometimes they will put it in water sometimes to disinfect water. Chlorine. So some of the trends of these group 17 elements that their reactivity decreases as you go downwards. So the top member, that's fluorine, is very reactive, as I mentioned. It's very, very reactive. The most reactive electronegative compound, fluorine. But as you go down, after fluorine, you have chlorine. Chlorine is reactive as well, but it's not as reactive as fluorine. When you go downwards again to bromine, you would start seeing that the reactivity is decreasing downwards. So the reactivity decreases as you go down the group. So that's one of the trends in this metal. So fluorine is the most reactive and iodine is the least reactive. So if they should ask you, I think I do see this stuff a lot. They'll tell you arrange them based on their level of reactivity or electronegativity. So in levels of the electronegativity, fluorine is the most electronegative, then iodine is the least electronegative. Sorry, fluorine is the least is the most reactive, while this guy is the other way around. It's most electronegative. It's the most electronegative. This one going downwards, iodine, bromine, they are seen to be less reactive. I don't know why I'm mixing my tongue. They are least reactive. Fluorine, the fluorine is higher in reactivity, while iodine them they are less reactive. So halogens they form ionic halides when they react with metals, and when they react with silicon, they form silicon chlorides. So they react very well with most elements on the periodic table. They react very well. You will see them reacting with group one, see them reacting with group two, see them reacting with even group three, group four, group five, group five elements. You will see them reacting almost every element on the periodic table. It reacts with group one, group two. Group one, you have sodium chloride. Group two, so after sodium is what they call it, aluminum chloride. So not aluminum, magnesium chloride. After magnesium chloride, we have aluminum chloride. After magnesium, we have aluminum. What's the next element? Self sodium, um, sodium, magnesium, aluminum, silicon. We have silicon. Phosphorus, we have phosphorus pentachloride. That's PCl5. Phosphorus, sulfur. Sulfur too reacts with chlorine, but though sometimes it's not really you will not really see the case of sulfur and chlorine in most cases. So they react with almost every member of periodic table. So that's why they're seen as one of the most reactive elements on the periodic table. So now going back to oxygens and sulfur. I don't know if I'm going backwards. Yeah. Going back to oxygen and sulfur. Oxygen forms oxides like CO2 and H2O. Sulfur forms dioxides, SO2 and SO3. And so if you look at these two now, sulfur and oxygen, they are on the same group, but they react with themselves to form oxides. So when they react themselves, they form oxides. When they react with other elements, they can form oxide when they react with oxygen can form oxide when it reacts with other elements. And also when oxygen reacts with sulfur, it can also form oxides also as well. So they form oxides, and these oxides are usually acidic oxides. I've mentioned that before. So they are used in industries very well, in several industries, both in the production of detergents, sodium lauryl sulfate, SLS, in production of detergents, fertilizers. They are also used there in batteries. Yes, I think there's some batteries that use sulfur. Some batteries that they use sulfur as part of the components or the type of ions in it. But I cannot remember one yet, but I think there are some batteries that do so. So that will be all for this lesson. That will be all for this lesson. I don't know if anyone has any questions so far. I don't know how much time we still have left. Oh, thank God. We still were able to meet up with time. So does anyone have any question so far? Can you guys still hear me?
I can hear you, sir. I don't have a question.
Okay, let's assume that no one has any question. So in the absence of any question, I think we'll be calling it a night now. And tomorrow we'll be having our next chemistry class. I think in that next class we'll be treating organic chemistry. Organic chemistry. I don't know how fast we'll be able to go through organic chemistry, but I think organic chemistry to me is even one of the simplest portion of chemistry to me. But let's just see. By tomorrow we'll see how far we are able to go in chemistry. In organic chemistry, which should be one of our last night class in chemistry. So that will be all for this evening's lesson. I think see you guys when next we see. So good night, everybody.